Hey folks, Michael Johnson with the Energy Sketch Live. I welcome. It's 2025-02-10, 10th of February on Monday at 12:12 p.m. And welcome. We're going to talk today about a specific challenge of decarbonization, and not just decarbonization. I mean, that's, there's like sometimes there's a hyper focus on like the carbon emissions and the decarbonization, but there are a lot of other related issues. I mean, local air pollution, environmental, degradation, fuel leaks, toxicity, associated impacts on local communities. Like, there's so many issues on top of just, let's say, quote, just the decarbonization. Good. I'm just doing some technical checks. It's a little bit different today anyway, behind the scenes. I couldn't get my other thing to work, but we got a webcam with the green screen. It looks a bit glitchy, but I'm down here in the corner. So, hey there, welcome. And cheers. Get your coffee, get your water, get your whatever it is, your lunch, and let's jump into it. Remote industries and villages. Oh, yeah, we got to do our disclaimer of the day. Disclaimer, hashtag disclaimer. So, right, I work in energy. All opinions are my own. No guarantees, no refunds. We strive for, technical accuracy, but we're just riffing. And so none of the numbers really should be trusted. Even though it's funny, I'm wondering what your reaction is on the other side when I give all of these heavy disclaimers. And I was talking with a friend recently, and he had this tendency to give heavy disclaimers like, I'm not an expert. I just read about this. I'm not really sure. There's a lot of different views. And I'm like, what are you going to tell me? Like, I'm already like building up this picture of like what you're going to tell me is like way out there. So I feel like for me, when I hear someone couch something excessively with all of these disclaimers and stuff, I'm like wondering like what's behind that. Like they don't really believe it. So I'm going to think about that. But again, we're just riffing, we're sketching in an order of magnitude sense and just storytelling. Let's pretend together we're just sketching on the chalkboard, the whiteboard, we're drawing stuff, and we're going to just riff on this topic of remote industries, remote communities, remote villages, and some of the energy challenges associated with those places. And we're going to riff on this paper. I'm happy to say that I was, yay, there's my name. I mean, what I like, not to like put the spotlight or anything, but I was super happy and excited, and so really blessed to be able to collaborate with these two folks amongst the rest of the Alternative Fuels Laboratory at McGill University. Again, disclaimer, right? Our company, Siemens Energy, funded this work through a collaborative research project, also funded by the Quebec government through PRIMA and the federal Canadian government through NSERC, where the industry contributions, and we worked with 4 other industrial partners on this. You can read all about it if you search for this paper, and we're going to sketch around some of the ideas here. Techno-economic assessment of aluminum, pellets of aluminum. So remember this, the idea here is that we store clean energy in pellets of aluminum. We send those to a remote location, way far off grid, and we store those in big hunkin' grain silos instead of storing liquid hydrocarbons like we do today, which can be stored in, simple steel tanks. But there's a lot of issues there with potential spills. It's volatile. It's toxic for human life, toxic for aquatic and terrestrial animal life, and yeah, generally we want to move away from those things. So aluminum provides a way not only to potentially decarbonize the remote industries and remote villages, but also to transport energy in a super simple, energy dense, clean, non-toxic. It won't spill, it won't leak, it won't degrade over time. It's transported by simple buckets, bulk carrier ships on the back of a truck, right? If you have an accident on your truck and you're carrying energy today, right, your diesel truck's gonna fall over, it's gonna open up, it's gonna spill everywhere, it's gonna catch fire, it's gonna wreak havoc. And we've seen this. Check out my other video on the Lac Mégantic rail disaster, where something like 70 rail cars full of crude oil from the back-end fields of Montana, no, not North Dakota, exploded in a small village of Quebec, and the implications of that. So we can move away from that to better ways of transporting energy. So yeah, we're going to have some fun, and we're going to show, first of all, we're going to go to Google Maps. I get sort of I have fun with Google Maps often. So what I've done here, I've just marked a few interesting remote industrial sites in Canada and one in Alaska. So there's a diamond mine, Raglan mine, they mine like nickel. Meadowbank mine, they mine gold. Baffin land, there's an iron mine, and this is a indigenous village in the north of Quebec. And over here, Red Dog mine, that's owned by Teck, and they mine zinc over there. So let's just pick one. Let's pick Red Dog Mine. And thank you to Tech for participating in this research work also. Again, all opinions are my own. Tech was a partner in this work and was funding it also. So it's interesting to, again, we zoom in on this. This is a remote off-grid industrial site. We're mining zinc. There's some deposits here. There's a road here. You can follow the road. It goes all the way. You kind of lose the road. There's the road. Goes all the way to the port facility. So I love just sometimes just exploring Google Maps along with other maps and maps of locations and remote industry locations. So look for these structures. There are 7 diesel storage tanks here. That's interesting. Like you need like summer diesel, winter diesel, right? Winter diesel is like a particular mix of diesel that's more resilient to issues in cold weather. It has a different mix of hydrocarbons, maybe some additives also that prevent it from clouding, prevent it from having lubricity issues, I think, typically in the cold season. So there's 7 diesel storage tanks here, right? And the rest of this is like where they bring the zinc um, oxides, the zinc ores and oxides that have been mined. They bring them here. It's processed, and there's this kind of conveyor belt that brings them out here and brings them onto the ship. And that ship would also bring in diesel fuel. So there's storage for diesel fuel here at the port. And again, we'll take the road, take the road, take the road all the way to the mine. And typically you're going to see, again, there's lots of storage, lots of shipping containers. That's the mine road, comes in. And there we go. There's, another 2 diesel tanks here, another 2 diesel tanks here. And typically also you're going to find at each of these sites, you're going to find a power plant somewhere. So if you look for some kind of smokestacks. It's hard to see smokestacks sometimes on Google because they're vertical, and you got to look for the shadows of the smokestacks. And you can search around also online for like a layout of the plant, something like this. So I'm not seeing directly off the top here the power plant, but there's surely a power plant here. There's a bunch of diesel gen sets that are running, that are providing electricity for the facility, and they're using also the diesel for the trucks that are going out and mining the stuff, and there's all the processing happening here. So that's like an example of an off-grid remote mine site with a pretty hefty electrical demand of, let's say, 25 megawatts is a sort of a typical um, value there of these remote sites. And let's maybe show another one slightly different. Whoopsie. Yeah, this village here. Let's zoom in on the village also. This is a indigenous village. I won't even try to pronounce the name. Typically, they're going to have an airport, and they might have some fuel storage near the airport, small fuel storage, or there's a sort of terminal there. But you're going to have fuel storage somewhere here. There we go. There's fuel storage right here. So typically a barge would come here, and they would like have a line that would connect here somewhere. And then you're going to have somewhere in here also, there's a gas station. There's going to be one, like in this case, it's going to be Hydro-Quebec. They're going to have a diesel generator somewhere providing electricity for for the village. And speaking of that, let's just jump to one other site here. There's another of the partners that we work with on this paper, Agnico Eagle. They're mining gold here in the Meadowbank facility. And if you zoom in, you should probably also see some fuel storage. Where's the fuel storage? Um, Here we go. There's fuel storage here, 2 tanks. And you can see better here the power plant. This is the power plant here. These 2 little jutting things out, there's 4 of them, 4 smokestacks with these sort of multiple things like that. This is the powerhouse here that's providing, again, about 20 megawatts electrical. And again, here, there's this road. There's a satellite site up here where they're exploring. And there's this road, goes down here to near Baker Lake, another indigenous community here, with, over here, diesel storage. And here's how the diesel arrives. This is a diesel barge. They've got a line here that snakes, goes through the water, right? They drop that. There's probably like a Zodiac that comes out, gets the line, brings it back here, connects it somewhere here. There's some pumping infrastructure. It pumps it and it stores it in here. And this has got to happen like a couple times a year, maybe, right? Because this is far north, and this river maybe is going to be iced over. So it's really, really remote, right? You got to have a big ship that comes here into Hudson Bay, and then it transfers the fuel to a barge, a river barge that's going to go up this river here and offload it here. So it's super complicated. And again, it's, you can read in the news, sadly, about accidents that happen. People that handle this stuff, yes, they are fully trained. They have kits for spills, but like shit happens. There's unknowns. Roads, can get um, damaged and all this stuff, and spills happen. So we want to move away from that on top of also decarbonizing this energy. So let's get into it, and let's sketch a few things here of kind of what we're talking about here. So this idea of decarbonizing the remote villages, the remote communities, right? We want to, let's just do a little, this is our left to right over here. Over here, there's industrial, this is a bad sketch. There's an industrial building here. They're grinding stuff. There's like trucks that are operating. There's a big truck here that's like mining all this material, right? There's like electric motors that are doing stuff. We need heat. So we need really 3 things here. We need heat, we need electricity, and we need motion. Let's call it mobility, right? For any mine site, remote industrial site, or village, really. I mean, people want to move around the village. They have cars, trucks, ATVs, vehicles. We need heat. We need to heat our buildings. We need to heat our processes, and we need electricity to drive all the things, all the appliances, all of the electrical equipment here. So this is our kind of, let's call it, our remote customer. And today, all 3 of these things, right? Today, all of these are diesel fuel, essentially. Diesel fuel is put into diesel generators to make electricity. Some of the heat from the excess heat from those diesel generators is used to heat. That's a nice like cogeneration type of thing. But also in the winter, when the heat demand is very high, diesel fuel is burned for heat, and diesel is used for mobility. So how do we decarbonize this thing? Because it's far away from the let's draw our little our little electrical grid here. Here's the electrical grid, electricity grid, right? How do we bridge the gap? That's the question. We want to bridge the gap. There's a gap here, and the gap is in both time and space. Even with diesel fuel, right? We mine, we process, we harvest diesel fuel, and we deliver it, and we use it later at another location over here on the right. So how do we bridge the gap and do it in a way that's clean and cost effective and ultimately, satisfies the requirements for society. So this is an interesting use case that kind of encapsulates a lot of the challenges here. So what we really want to do, we want to decarbonize this, and we want to make it clean and safe, a safe form of energy that we can transport into the remote customer. So over here, we've got our energy. Let's draw our little wind turbines. We've got wind. We've got our solar panels. Solar plus other, let's say, other clean electricity, whatever that is, nuclear, or other. So we want to harness this and harness this into a fuel. And this is what we call like power to X, where X is a type of fuel that we can produce with electricity, which is the kind of the paradigm shift that we're undergoing right now. Right now, today, we use fuel that we get long ago stored and converted solar energy in the form of fossil fuels. We dig that out of the ground, suck it up under the ground from underground, and burn it to produce electricity. Instead, what we want to do is the paradigm shift is that we want to harvest the abundance of clean electricity and use chemical processes to convert that power into X. And the X is a new fuel that we want to make. And so there's a lot of talk out there that you may have heard about things like hydrogen. So hydrogen is one of these these fuels. We can use power to make hydrogen via a process that's called electrolysis, typically water electrolysis, different types of technology of water, essentially using an electric current to split the H2O into H2 and O2, hydrogen and oxygen. The challenge for using hydrogen directly for this type of remote thing is that it's hard to store. To transport it, it needs to be like liquefied, compressed. It's not very energy dense in a volume basis, so it needs to be compressed to high pressure, and even then, still, it's challenging to store and transport. So then people are talking about going to other things like NH3, which is ammonia, which is yeah, easier to transport. It liquefies at only like minus 33 degrees Celsius or at moderate pressures. But the risk there is that it's even more toxic, right? So again, trained personnel would be transporting the ammonia, but shit happens, particularly in these remote customer locations, like way the hell off grid in the Arctic villages, right? So it's great, it's decarbonized, but it's not likely to be very good for this type of application. Where you've got to transfer things from ships to barges, bring them up sensitive rivers, sensitive aquatic and terrestrial ecosystems. So the breakthrough, really, that McGill Group is working on is using these metals, and these are things like iron, which I've talked about previously, or in this case, aluminum. So what we do, and we'll talk specifically today about aluminum, we take this power and we bring it into, again, an electrolysis facility. I'll just draw this here like this. We do aluminum electrolysis. Aluminum is made by electrolysis. It's a process where we take in, let me put it this way, aluminum oxides are brought in, and we add electricity, and then we produce aluminum pellets. Let me draw this little pellet here. This is a tiny little pellet or a granule, and it's like this big. The stuff they're working on in the lab is like a little 3 millimeter pellet. You can hold it in your hand. It's totally safe, inert, non-toxic. It won't spill, it won't leak, it won't degrade over time. It can be transported in regular bulk carriers anywhere around the world, cheaply and safely. And the breakthrough that McGill is working on is this reactor that takes in the aluminum pellet along with water, H2O. Let's call this a reactor. So aluminum plus water yields hydrogen plus heat, as well as the aluminum oxides that are filtered out of this process. This is really the breakthrough invention from McGill University, the reaction of aluminum with water, and it happens at what's called supercritical water conditions. So that's something like, what is it, 400 degrees Celsius and 200 bar of pressure. So the breakthrough that McGill discovered there is that the supercritical conditions of the water can break through the protective layer. So you think about this little tiny pellet. It has a nanometer sized protective layer of aluminum oxides that forms very rapidly when it's exposed to the air. And that has the function that it protects the rest of the pure aluminum inside from breaking down or reacting. So other people have investigated this type of reaction by reacting it with like sodium hydroxide or adding other metals like gallium or indium, these sort of specialized rare metals that catalyze that and help to break down the layer. But that makes that pellet dangerous to transport because once it meets water, it's going to react immediately. So the breakthrough with this invention is that you need to expose that pellet of aluminum to the supercritical conditions that it only exists inside this reactor. So this aluminum pellet over here is completely safe, inert, non-toxic. It won't spill, it won't leak, it won't react. And that this is what is transported to the remote site. Reacted in the reactor produces this hydrogen and heat. And then the heat is good. That serves like check mark. That's one of the solutions that you need there. The hydrogen can then be used to make power via some kind of engine, fuel cell, gas turbine, gas engine, anything like that. And it can also be used for the mobility of the trucks. Or the power can also be used for the mobility. Depends on the use case, depends on the power needs, the range, all of these things, right? We have electric vehicles, electric cars, trucks, kind of mining trucks. They're like huge ass beasts of a thing. Right? I mean, we do electric mining vehicles, typically underground, and battery costs are coming down significantly with time, but there is significant challenges there. So the hydrogen can be used for power and mobility. So this is a sort of an open question here of what do we do with the mobility depends on many factors and depends on the logistics of the thing. So the breakthrough here is that we take clean energy, wind, solar, or other. We produce aluminum pellets by electrolysis. We produce them in small pellets. These things can be transported from our source to our remote customer over here. The breakthrough invention is that this reaction takes in the aluminum with water locally available, can be dirty water, maybe mine water potentially would be a super awesome breakthrough. Reacted in the reactor produces hydrogen heat. The hydrogen can then be used for some combination of power and mobility for the trucks. And we've gotten away from the challenges associated with transporting and storing hydrogen and ammonia also. We've gotten away from the toxicity of the ammonia by simply transporting and storing inert, safe, non-toxic pellets of metal. So let's jump into the article. I'll just this thing is freely available on the web. And yeah, we'll jump into a few interesting sections. So we talk about aluminum as a carrier. We go into the details of aluminum production with the over voltages and all this stuff, and super detailed discussion of this. The recharging power to aluminum. This is a nice little summary of the thing, right? We take clean energy in on the left. We have an aluminum smelter where we produce aluminum. You would send up half a ship's worth of aluminum pellets, store them in a simple grain silo, react them in the reactor, and then release the heat and hydrogen via a power plant into power. Then the oxides would get collected from another grain silo, right? These grain silos are super cheap, simple to install, and both the aluminum and the aluminum oxides are safe and simple to transport. So you'd have a full ship worth of aluminum oxide coming back on the other trip. That is potentially an issue with this. It's different, right? With diesel, you send a ship full of diesel and it comes back empty, right? With the aluminum, you send up half a ship worth of aluminum. It's got to collect some of the oxides to come back, so that there is a circularity there, which does impact probably the logistics of a site. So there's some transition required into this new way of operating. So we're going to show maybe this graph. Are we showing this graph a bit later? Yeah, here we go. Let's show this graph here. This is an interesting graph. So I was talking about that paradigm shift now, where instead of taking fossil fuels out of the ground, burning them to make power, we are flipping that around. We are harvesting clean power, carbon-free power via wind, solar, or other means, and using that power to produce fuels. And this is a graph that shows the way of thinking about this, which plots the energy cost versus the electricity cost. And so let's make a new little section over here where we're going to talk about that and what that means. We're going to sketch it here. So again, this graph plots electricity cost. Let's say in dollars per megawatt hour electrical, and we want to take, this is our input. This is our input. Our output in this case is fuel cost. Again, in dollars per megawatt hour, let's call it chemical in this case. So there are two things to consider, and I'll sketch a little thing here. We have the electricity that comes in. We have a big facility here. This is our fuel production facility, and then outputting there we have fuel. So we want to consider this thing, and it has a capex, which is initial investment that you need to pay on day zero to build this whole equipment here. And there's two essential characteristics of this thing. There's capex and there's the efficiency, which would be basically the, right, you've got, let's say on a power basis, you've got kilowatts of electrical coming out, and you've got kilowatts chemical of the fuel coming out. And I would consider this, let's say, lower heating value of the fuel. Engineering jargon, blah, blah, but essentially this would be the ratio of kilowatt chemical to kilowatt electrical. And for typical processes like hydrogen or others, it's, well, you know, I don't know, around like 60%, 65, 62, maybe less, maybe more. You know, it's an order of magnitude, let's say. So there are losses associated with this process, which is normal to be expected. It's, you know, thermodynamics. We're converting energy from one form to another. There will always be some losses associated with that. But, you know, the benefit that we get from that, and this should not be used in all cases. I mean, another thread for another day is like electrify everything, right? We want to electrify as much as we can of industrial processes, but there are still some that will need fuels, and these remote industries are a case where we will need some fuel because it's not feasible and it's extremely high cost, and it would be destructive to build like power lines from, you know, the current electrical grid, thousands and thousands of kilometers to like a remote mine site. It would cost billions of dollars. So we're better off producing fuels on the electrical grid, sending those to the mine site because they can be stored for long durations of time, right? There's a cost associated with this, but there's a benefit because the fuel can be burned at another point in time. It comes back to like energy storage and various other threads that we'll get into another time. So there's two key characteristics, a capex and an efficiency. So you think about the fuel cost versus the electricity cost. And we start here at zero. Like even if your electricity costs nothing, you would still need to pay for the CapEx. So this line here essentially represents the capital investment cost. So even if your electricity was free, you were getting it for nothing, the fuel would still have a baseline cost that would be the required amortization of those capital expenses plus any associated fixed operational and maintenance costs. Then if we start moving down this axis here, we're going to have some kind of slope here. And this slope is function of the efficiency. The lower the efficiency, the steeper this graph is going to be. A lower efficiency is going to have it like this. A really high efficiency would have it like this, because that means that you're using more efficiently the electricity at this cost, right? If I'm more efficient, then my fuel cost is going to come down. If I'm less efficient, my fuel cost is going to go up. So the idea, and that's this plot here. We're plotting essentially the energy cost versus the electricity cost. And these are some of the alternatives that are considered. There's like hydrogen, ammonia, aluminum, and we won't talk about this for the moment. So let me go back here. So we could call this, let's call this like the base. The base that people are talking about mostly these days is hydrogen. But again, hydrogen is inappropriate for this type of remote, very remote, off-grid as an energy transporter and an energy carrier because of the challenges around its storage and transportation. So we want to add something to this setup here. We want to further process the hydrogen into something else, and this might be something like ammonia, or if you liquefy the hydrogen, it would be LH2. And there's another, and you can see there's another line here. This uncertainty zone here is the aluminum. So there's a kind of another zone here, something like this. There's like aluminum. Aluminum might be in this range here. So that's the interesting, and you can plot other ones. There are others to add. Things like methanol is another chemical that's being talked about, although the challenge there is that it does contain carbon, and so it depends on the source. And we'll get into this maybe in another thread, but there's also things like iron. So then what you can do is, if we come here, I'll just erase this. We'll get to that maybe another time, right? So where are you going to be on this graph? Well, that depends. Where are you in the world? What is the cost of clean electricity in your part of the world? A whole other conversation there. But you pick where you are roughly, and then you go up, and then this is your cost. This is your cost of fuel. So that's just the first part of this chain. And we made a nice, I really love what Pascal did here with the nice value chain here. Let's just take this and we're going to sketch around this, the whole value chain of this concept. So let's bring that away, paste this, whoopsie, paste this in here. That's good. Let's zoom it in a little bit. Yeah, so you can see all of the similar processes that need to be done here with these concepts. There's the power to X up to here. So we're taking in here, we've got electricity, we've got wind, we've got solar that comes in as an input. Then we do these electrolysis processes, liquefaction in the case of hydrogen, or the Haber-Bosch synthesis in the case of the ammonia. And if we consider here, that's where we got to with this fuel versus renewables chart. So here, that's our fuel cost at this place. Then we need to transport it. There's a cost associated with every single step of this process. There's a cost associated with this, right? And the breakthrough here is that this is like really low cost. This is just a grain silo versus a cryogenic liquid hydrogen storage facility that you'd see at Cape Canaveral, because hydrogen is used as rocket fuel today, right? Ammonia is cheaper. Then hydrogen, which is one of the breakthroughs there of using ammonia, is that it's more simple to transport than the liquid hydrogen. But here, this is really, really low cost. And then, like I said, you have the metal-water reaction, and you make power at the end. So in the paper, we compared all of these vectors together and arrived at this chart here, which shows the overall costs. Let's just get into this thing right now. Over here. Okay, so what can we notice from here? Electricity generation cost for each option, right? This is the electricity cost, a bar chart. Liquid hydrogen, ammonia cracked back into hydrogen. I didn't really get into this. We could get into it another time. Well, anyway, I'll just show you briefly. The idea is that hydrogen is difficult and complicated and expensive to store and transport. So instead, we turn it into ammonia, which is simpler and easier to transport and can use existing infrastructure like liquefied petroleum gas carriers and things like this. So we put that on a ship and we transport it around the world over to the customer. But the customer has a gas turbine or an engine that only can burn hydrogen. Burning this directly does not really exist today. It's complicated, there's slip, and it's toxic, and it doesn't burn well, very low tendency to burn, so you need to completely redesign your combustion systems. So this is why we have this idea of a cracker. So you can think of ammonia as a kind of a nut that holds hydrogen inside. You apply high heat to it and it cracks and it opens into, it goes into nitrogen and hydrogen. And so to be completely chemically balanced here, we'd have two of these and we'd have three of these. Two ammonia molecules goes into three hydrogen molecules and a nitrogen molecule. Then you can burn that in the gas turbine and produce power. So this is the option that we're showing here. The problem is that this thing costs a lot of money also. Right, it would be cheaper to just directly burn the ammonia here. That's actually like the best option among the four, but there's significant challenges associated with it. So aluminum is here. That's the final cost. And you see like this compared to diesel, right? Diesel is like super damn cheap, right? And so to be at the same cost point, we would need to have a carbon tax of $360 per ton CO2, which is like really high. I don't think this exists anywhere in the world. In any of these trading schemes or carbon tax, carbon prices. That's a whole thread for like another edition maybe of the energy sketch, and maybe it would be interesting to get an expert on here. We just jase and just riff around carbon pricing and carbon and tax, and there's this whole like rhetoric around, well, from the Conservative Party of axe the tax, but essentially like the carbon tax in Canada is not well understood. I don't understand it, but apparently it's good for citizens because they ultimately get a refund, so a rebate associated with it. So, I mean, we want to incentivize with carrots and with sticks. So putting a price on carbon is an appropriate carrot. But it just shows that that carrot needs to be pretty steep relative to where it is today for any of these options to make sense. But among these options, 1, 2, 3, aluminum seems to be in the same ballpark, probably better than liquid hydrogen because of the high capex costs of the storage and the transportation, and probably similar, comparable. There's some trade-offs associated with it relative to the ammonia cracking due to some efficiency impacts of the aluminum power cycle. So that's what we had to talk about today, folks. What's the time? 12:51. Yeah, I want to stop it at at least 12:55 to give a chance to go have a lunch and get back to our day jobs. So that's well, let's just do a little retrospective here. So we talked about power to X, the whole little cycle here. We want to deliver fuel to our remote customer. We talked about roughly this sort of like fuel production Let's go here. We talked about fuel production as a sort of a black box here with power comes in and fuel goes out. CapEx and efficiency are the important metrics of that. And we can plot the performance of that on this graph of fuel cost versus electricity cost with these lines that represent two things. Roughly the CapEx and the fixed OpEx brings you up to here, and the slope of this line is associated with the efficiency. So if hydrogen is sort of the simplest sort of base chemical that we can make in this way, then we can add on top of this to liquefied hydrogen, ammonia, iron in that family, and also aluminum is somewhere in this family. So they're all different. They all have different, pros and cons associated with them. But, personally, and this is my personal opinion, is that I'm really jazzed and excited and very positive around the metal fuel ecosystem that's building up here as a way to transport and store chemical energy, which is represented on this value chain here. You take clean power on the left, you do the power to X, you produce the fuel here. And the case of aluminum here, the fuel is pellets, non-toxic, safe, inert, simple and easy to transport. It won't spill, it won't leak, it won't degrade over time. And it's transported in these simple bulk carrier ships, the cheapest ships on the planet, really. It's just an empty hull where we transport a multitude of things like grains, ores, anything that's sort of like high volume, low mass, building materials, all this stuff, multi-purpose bulk carrier ships. Instead of these specialized ships like hydrogen, there are very few hydrogen carrying ships in the world today. There was a pilot program in Japan. They made one ship that carried a minuscule quantity of hydrogen. So I'm sort of skeptical that this would really scale up and that the costs would really come down, whereas this is extremely mature, costs have come down, and very simple to make. These also exist in the world, but again, the concerns on the toxicity of the ammonia and the high capex that's required for this step, the cracking of the ammonia. Then that stuff needs to be stored, and here we just have simple, cheap grain silos, really just a grain silo where you would store your pellets of metal, react them in the metal water reactor, and make power. And on other threads, this is right where Canada has an advantage that we already have a lot of aluminum production today. And in the future, we could be harnessing our abundant solar and wind energy resources and just pumping out metals and transporting those, trading those around the world by ship, by truck, by train around the world. There's, no need for pipelines with this, right? That's part of the energy conversation in Canada, is that we're kind of hamstrung by the lack of east-west pipelines. There was a lot of resistance to like the Energy East pipeline many years ago. Now I think François-Philippe Champagne is back. He's like, oh, well, maybe we should reconsider that. Let's make metals instead. Let's make metals, folks. So that's what we're going to talk about. I'm going to keep hammering away on this. So that's the paper, Techno-economic Assessment of Aluminum as a Clean Energy Carrier to Decarbonize Remote Industries. Thanks so much for tuning in, folks. And how do I end the stream? I don't know. I got to go back to my OBS window, and I'll just give you a little energy sketch. Energy sketch was live today, and thanks so much for tuning in, folks.